Hello everyone, my name is Ming. I am from section 2. Today I will be presenting about my project 2, which is a study on the secondary data of car specifications. To start off, we know that cars are very important in our daily life because we drive cars to school, to work, to buy groceries every day. Hence, we can travel easily and conveniently with cars. For my aim of study, I wish to apply and perform statistical test analysis such as two-sample hypothesis testing, correlation analysis, regression analysis, and the chi-square test of independence on a secondary data source. I also hope to prove whether the selected variables are dependent on each other or not. A little bit about the background of our study. This dataset is actually a secondary data source that I retrieved from the KEBARANKALIAN website. The data was collected by Eleanor Shu, who works as an analytic from the United States of America. So these are the test analyses that I will be performing. For two-sample hypothesis testing, the variables that I have selected are aspiration and horsepower, where I will test whether the mean horsepower of turbo-aspirated cars are higher than the mean horsepower of standard aspirated cars. For correlation analysis, the variables that I have selected are engine size and car price, where I will be testing on whether linear relationship exists between variables engine size and the car price. For regression analysis, I have selected engine size as the independent variable X and horsepower as the dependent variable Y, and I will test on whether the value of horsepower depends on the value of engine size. For goodness of fit test, also known as the one-way contingency table, I have selected variable field type, where I will test whether there is difference between the observed frequency and the expected frequency for the field type used by cars. Lastly, for chi-square test of independence, or also known as the two-way contingency table, the variables selected are num of doors and aspiration, where I will test on whether the number of car doors and car aspiration are related. For two-sample hypothesis testing, test on mean, we want to test whether the mean horsepower of turbo-aspirated cars are larger than the mean horsepower of standard aspirated cars at confidence level 95%. So firstly, we group the mean, standard deviation, and the observed frequency of turbo and standard aspirated cars in a table as shown on your left. We first state the hypothesis statement. For null hypothesis, mean 1 equals to mean 2. Whereas for alternative hypothesis, mean 1 larger than mean 2. Next, we'll find our test statistics T by using the formula as shown below, and we'll get test statistics T equals to 4.0804. Next, we find our degree of freedom V by using the formula as shown below, and we'll get V equals to 64.711. And finally, given confidence level equals to 95%, hence, we find our T critical value by looking from the T table, or you can also calculate it by using RStudio as shown below, and we will get T critical value equals to 1.669. Now we state the decision. Since test statistics equals to 4.0804 is larger than our T critical value, which is 1.669, we reject the null hypothesis. For conclusion, we have sufficient evidence to conclude that the mean horsepower of turbo-aspirated cars is larger than the mean horsepower of standard aspirated cars at alpha equals to 0.05. We can also visualize our data in a box plot as shown on your bottom right. This is how we perform the two-sample hypothesis testing by using RStudio. My second analysis is the correlation analysis, where I will test whether there is linear relationship between the engine size and the car price at confidence level 95%. Since both variables engine size and car price are ratio type data, we will be using Pearson's product moment correlation coefficient. Firstly, we state the hypothesis statement. For the null hypothesis, rho equals to 0, which means that there is no linear correlation. Whereas for the alternative hypothesis, rho is not equals to 0, which means that there is linear correlation. Next, we'll find the correlation coefficient R by using the formula as shown, and we'll get R equals to 0.8731717. Next, we find our test statistics T by using the formula as shown, and we'll get our test statistics equals to 25.5241. Next, we find our degree of freedom. We'll get our degree of freedom equals to 203. Since we are using the two-tailed test, we have two critical values here. From the t table, we'll find that our lower tail critical value t is equals to negative 2.25815, whereas our upper tail critical value t will be equals to 2.25815. Now we state our decision. Since test statistics equals to 25.5241 is larger than our upper tail critical value, which is equals to 2.25815, we reject the null hypothesis. We have sufficient evidence to conclude that there is linear correlation between the engine size and the car price at alpha equals to 0.05. We can also make a scatter plot as shown below by using RStudio. On your bottom right corner is how we perform the correlation analysis using the RStudio. My next analysis is about regression analysis, where I will test whether the value of horsepower depends on the value of engine size, using engine size as my independent variable x and horsepower as my dependent variable y. Our linear regression model equation should look like this. And by using the formula given, intersection coefficient B0 equals to 6.7133 and our slope coefficient B1 equals to 0.7698. Next, we'll find the values of explained and unexplained variation. So from the given formula, we can find the values of the sum of squares regression SSR, total sum of squares SST, and also the sum of squares error SSE. And finally, by using SSR divided by SST, we can get our coefficient of determination R squared, which equals to 0.657. Before we carry out the t-test, we have to find the values of standard error of estimate and also the standard deviation of regression slope. Now we can do the inference about the slope by using t-test. First, we state the hypothesis statement. For our null hypothesis, there is no linear relationship between engine size and the horsepower. Whereas for the alternative hypothesis, linear relationship exists between engine size and the horsepower. We have two critical values t here, where our lower tail critical value equals to negative 2.25815. Whereas our upper tail critical value equals to 2.25815. By using the formula given, we will find that our test statistics t equals to 19.7197. And now we state our decision. Since test statistics equals to 19.7197 is larger than our upper critical value, which is 2.25815, hence we reject the null hypothesis. We have sufficient evidence to conclude that the engine size will affect the value of the horsepower at alpha equals to 0.05. So to finalize, our linear regression model equation will be the estimated value y equals to 6.7133 plus 0.7698x. And when we perform linear regression by using RStudio, these are the following steps. Firstly, the LM function. Next, the plot function. And finally, the appline function. My fourth analysis is the goodness of fit test, where I will test whether there is difference between the observed frequency and the expected frequency of the field type used by cars at confidence level 95%. So firstly, we will state our hypothesis statement. For our null hypothesis, we claim the proportion of gas fuel type cars to be 0.85, whereas P diesel equals to 0.15. And for our alternative hypothesis, at least one of the proportions will be different than the claimed value. Next, we'll calculate our expected frequencies by using the formula n multiplied by p. And from the expected frequencies, we can then calculate our test statistics x squared, which equals to 4.4213. And finally, from the chi-square table, we can get our critical value x squared, which equals to 3.841. So now we'll state our decision. Since test statistics x squared equals to 4.4213 is larger than our critical value x squared equals to 3.841, hence we reject our null hypothesis. We have sufficient evidence to conclude that there is difference between the observed frequency and the expected frequency of the fuel type used by cars at alpha equals to 0.05. For my fifth and final analysis, it is about the chi-square test of independence, also known as the two-way contingency table, where I will test whether the variables number of car doors and car aspiration are related at confidence level 95%. Now we state our hypothesis statement. For our null hypothesis, there is no relationship between the variables number of car doors and car aspiration, whereas for our alternative hypothesis, number of car doors and car aspiration are related and dependent on each other. So, given that alpha equals to 0.05 and our degree of freedom equals to 1, we can find that our critical value x squared equals to 3.841. And now, we will calculate the expected counts for each cell. And from there, we can calculate our test statistics x squared, which equals to 0.5918. Finally, we state our decision. Since the test statistics x squared equals to 0.5918 is smaller than our critical value x squared equals to 3.841, hence we fail to reject our null hypothesis. There is insufficient evidence to prove that there is relationship between the variables number of car doors and the car aspiration. We use the chi-square.test function in RStudio to perform the chi-square test of independence. There are a few conclusions that I get from the 5 analyses. Firstly, I found out that the mean horsepower of the turbo aspirated cars is larger than the mean horsepower of standard aspirated cars from the 2-sample hypothesis testing. Next, I found out that there is a relatively strong positive linear relationship between the car engine size and the car price. For the regression analysis, I found out that there is a positive linear relationship between the car engine size and the car horsepower. For goodness of fit test, there is difference between the observed frequency and the expected frequency of the fuel type used by cars. And finally, for our chi-square test of independence, I found out that the variables number of car doors and car aspirations are not related and independent to each other. I think this is the end of my presentation. Special thanks to our lecturer Dr. Chan for his guidance throughout this project, and thank you. Bye bye.